Yeah, my name is Dr. Rajesh Prasad. I am currently working as professor in CSE department at AKGC Ghaziabad. So, today I am going to discuss about NP completeness and approximation algorithm. So, in this, what we are going to discuss is a problem which is in class P category, and another problem is like NP category, and one is in NPC category. So what is P? Class P problem. Class P problems are the problem which can be solved in polynomial time. So P is stand for polynomial times. Yeah, polynomial. Yeah. So any category of the problem which can be solved in polynomial time, like C, sorting. Most of the sorting algorithm, they can be solved in polynomial time. It's either linear or sometime quadratic and so on. So any problem which is going to be solved in polynomial is classified in P category. Another set of problem which is non-deterministic polynomial. NP stand for non-deterministic polynomial. Non-deterministic polynomial. That means the problem which cannot be solved in polynomial time, but given its a solution, we can verify the problem in polynomial time. Okay. So next category of the problem is NP complete. That problem is NP, and any other problem which is hard enough cannot be harder than the problem itself. So these are the category of the problem. Of course, any problem which is NP in NPC cannot be solved in polynomial time. Of course, they are going to be solved in some exponential time, let's say 2 to the power n, and other time they cannot be solved in polynomial. So next, so what is solution? So we can get approximation algorithm. So approximation algorithm are the algorithm which is not giving exact solution, but they can solve the NP and NPC problem in near optimal solutions. So in this approximate, will be defining approximation ratio and some related problems. Related problems will be the vertex cover problem, TSP, and set covering problems. So let's understand. So NP completeness. See, so almost all the algorithms we have studied so far have been polynomial time algorithm. Like see. So what do you mean by polynomial time? That any problem which can be solved in order of n to the power k. K is any integer, right? So example is like bubble sort, linear search, matrix chain multiplication, etc. For example, see, we have shortest path problem, shortest versus longest simple path. And we know that we can solve the shortest path problem even in negative edges in order of VE time, like Bellman-Ford algorithm. Bellman-Ford can solve the problem of shortest path into the order of VE, where V is number of vertices and E is number of edges, right? So, however, finding a longest simple path between two vertices is difficult, is not like impossible, it is difficult. This means that it cannot be solved in polynomial time. This cannot be solved in order of n to the power k. So, that means shortest path problem is polynomial time solvable, but longest path problem is not solvable in polynomial time. So, second category of the problem is Euler versus Hamiltonian cycle, Hamiltonian tour. We know the definition of Euler tour, and Euler tour of a connected directed graph is a cycle that traverses each edge of G exactly once, right? Although it is allowed to visit each vertex more than once, like in the Euler circuit, right? You have to traverse each edge exactly once, right? Each edge exactly once. However, in this process, vertex can be visited more than once. So this problem can be solved in order of e time. E is number of edge. This means it is still in polynomial time. Second category is Hamiltonian cycle, right? So you know that in Hamiltonian cycle, you are going to visit every vertex, right? Every vertex exactly once. In this process, like you can, yeah. So you see, it is a simple cycle that contains each vertex in V. And we know that getting Hamiltonian cycle is not going to be like in polynomial time. So this is going to be categorized in NP complete problem. So this is going to be solved in exponential time. So yeah. Next important category of this NP completeness is 2CNF, 2CNF and 3CNF. What is CNF? CNF is conjunctive normal form, right? And we know that conjunctive normal form means like conjunction of disjunction. So this is conjunctive normal form, conjunction of disjunction. This is how we define, right? So conjunction, this is the conjunction and this is going to be disjunction. So like where the term within the bracket can be either as it is or it can be in the form of negations, right? So a Boolean formula contains variables whose values are either 0 or 1. Boolean connective and or and not and parenthesis. So a Boolean formula is satisfiable if there exists some assignment of the values 0 and 1 to its variable that causes it to evaluate to 1. Clear? So yeah, so a Boolean formula is in case CNF, or we call it case CNF if it is the AND, right, AND of classes of R's of exactly k variable. So if we talk about 2CNF, that means this is AND of here and this is AND of here, this is AND of here. So in 2CNF, right, suppose we are talking about a variable in three terms, x1, x2 and x3. Here we cannot have more than two terms. Here we cannot have more than two terms. Even here we cannot have more than two terms, right? So that this is like 2CNF. So this can be written like x1 or not x2 C, and we can write like C x2 and not x3. This can be written or, and this x1 and x1 are, let's say, not x3. Suppose, so this formula is in 2CNF. Question is that, see, so we have three variable. This is the one, this is the one. Question is that this is in 2CNF and we are going to check, can we assign some values to x1, x2 and x3 so that its answer is evaluated to 1. Yes, we can do it in polynomial time if it is only conjunction of the this disjunction of only two variables, right? See, so you can see here x1 if you assign 1, x2 0, x3 1. So x1 is 1, so this means 1, right? Or x2 means 0, so this will become not x2 1. Okay, so not x1 means it is 0 or x3 means 1. This is also going to be 1. Clear? And this is also going to be 1. So not x2, similarly x2 is like 1 or not x3 0. So this is also going to be evaluated to 1. So ultimately we can see that 1 and 1 and 1. So ultimately we are getting its value to be 1. So assigning such type of values is like can be done in polynomial time if we are having only two variable within the parenthesis. However, if we are increasing from more than two variable, problem cannot be solved in polynomial time. So it will be converted into NPC problem. So this is important problem. 2CNF satisfiability versus 3CNF satisfiability. Okay. So next important task is how to show that a problem is NP complete. There are steps behind it. So if any problem is given to us, suppose we have any problem, let's say problem is like problem is this, right? So if you want to show that this is NP complete, there are some steps. Okay, first one, we have to convert this problem to the decision problem, right? In we have now two types of problem. If you talk about problems, we have optimization problem and second one is decision problem. So we have two problems, decision and optimization. In optimization, we are maximizing or minimizing certain values, right? But in decision problem, our answer is always going to be 1 or going to be 0. In decision problem, outcome is either 1 or 0. So first step is that in NPC, convert any optimization problem to the decision problem. Our objective is simple, that whether problem can be solved in polynomial time or not. So answer is 1 or answer is 0, right? See. So we are not interested in optimization problem. So first one, reduce the problem to the decision one. So for example, suppose we have a problem, let's say shortest path. So if this shortest path is optimization problem, where we are interested in finding the shortest path from source to the destination with some minimum cost, right? So we are given a directed graph G and vertices U and V, and we wish to find a path from U to V with usage phi stages. So right, so you can convert into this like shortest path problem to the decision, let's say path, right? So you are given G and U, V and V. Question, give K another number. K is the number of edges. So question is that, is it possible to have a shortest path from source to U to V with K number of edges? Yes. So answer is yes or answer is no. So this problem is being converted into the decision problem. So answer of decision problem is always going to be 1 or 0. So we convert optimization problem to decision. So number one is very simple, that okay, so you convert optimization problem to decision problem. This is step number one if you want to show a problem to be NP complete. Number two is like reduction. This is the important step. This reduction is the second step, right? Let me just clear one solution of this. Suppose you have a problem like C, ax square plus bx plus c equal to 0. Suppose this is the problem. It is a quadratic equation. So suppose you are interested in finding solution of this, right? And we know that solution of this problem can be solved, can be given in polynomial time, right? This is just like very simple problem of solving the quadratic equation. We know that this can be solved in polynomial time. And suppose somebody is asking the solution of bx plus c equal to 0, right? We know the problem, this solution of this problem, but we are interested in getting solution of bx plus c equal to 0. So see this bx plus c equal to 0, this can be converted into 0x square plus bx plus c. And this conversion takes place in time, polynomial time. So this is polynomial time. So it's very simple. That means if this problem is going to be solved in being converted into this problem in polynomial time, and this is already solvable in polynomial time, so overall problem is going to be solvable in polynomial time. So this reduction is very, very important. So means that you want to get this problem solution of this p dash, right? And from this p dash you can convert into the p using polynomial time. Like see, this is the p dash problem, and you took polynomial time to convert into 0x square plus bx plus c equal to 0. This is polynomial time. And we know that this problem can already be solved in polynomial time. That means yes, this can be solved in polynomial, this can be solved in polynomial. That means its answer is yes, its answer is no. So overall problem can be solved in polynomial time. So this is very simple. Yes, see this. So suppose we know that polynomial time algorithm to decide B, like C, we already know the problem of this ax square plus bx plus c equal to 0. Yes, no, we are already aware, right? Now question is that we are interested in finding solution of bx plus c equal to 0. We are interested in finding solution of this. So this being converted into this by adding just 0. So this conversion took time p, this is already taking p. So overall problem can be decided in polynomial time. So this is important step in showing a problem to be NP complete, right? So let's define polynomial time in mathematical sense, right? So another like notation of in polynomial in P, NP and NPC category is concrete problem. Any problem is said to be concrete if its input is taken from 0 to 1. So in NP complete solution, we are interested in taking 0 and 1 input from 0, 1 only. We are not interested in continuous input. We are interested only input from 0 to 1. So what is complexity class P? This is the definition. All the languages over 0 and 1. If there exists an algorithm A that decide L in polynomial time. That means here in order to show a problem to be P, first convert that problem into 0 and 1 and then find out any algorithm A which can decide that problem in polynomial time. Clear? So this is class P category. And second one, NP problem like not deterministic, non-deterministic polynomials, such type of problems, they cannot be solved in polynomial time, but if given its solution, we can verify the problem in polynomial time. See, so that means there exists a verification algorithm, right? So which can solve the problem in polynomial time. Yeah, verify the solution in polynomial time. For example, suppose like we are given like a Hamiltonian cycle, right? So if somebody like this is the graph, okay? Yeah, suppose this is graph number 1, 2, 3 and 4. Question is that whether graph is having Hamiltonian cycle, let's give them the order of the vertices 1, 2, 3, 4. This is solution which is given to you. Now you need to check whether this solution is forming a Hamiltonian cycle or not. So if you start from here 1, then 2, then 3, then 4. Of course, yes, this is giving this Hamiltonian cycle by adding 1 in the last. We know that in cycle starting and ending should be the same. So that means we can verify into the polynomial time. So this verification is known as certificate. This Y is known as certificate. X is the input which is going to be the graph, right? And remember, for this NP, our problem should be in concrete problem. That means input should be taken from 0 and 1. So this Y is known as a certificate, right? So if we can get certificate in polynomial time from this input, which can verify yes or no, that means problem is in the NP category. See, so what is class NP? Class NP is like concrete problem. Again I said that concrete problem should be in concrete means input should be 0 and 1. If there exists a certificate, remember that certificate should be like available in polynomial time. Just like you saw the vertices are given. So if this certificate is given in polynomial time such that there is an algorithm which can decide based on this input and this is the certificate. if it can give the answer as 1, so that means yes, we like this problem is in NP category, not polynomial, but can be verified in polynomial time, right? So yeah, so third category is of course P is subset of NP. All problem which can be solved in polynomial time can also be solved verified in non-polynomial time. So that means P is subset of NP. So this non-polynomial, non-deterministic polynomial is bigger version of the P. This is the first thing. Third category is NP complete. Yeah. So a language is NP complete, right? If first one, it is NP. That means given the certificate, it can be verified in polynomial time. And second condition is that all the languages can be polynomially time reducible to L. This is the language we are checking for its completeness. Any other language can be polynomially reducible to L. That means no one is like harder than L. See, for every L dash belong to N category. So we are interested in checking completeness of L. So any L dash category which is of course NP category can maximum be reduced to L. So this L dash belong to NP category. Clear? This L dash belong to NP category. So you see, these are the two conditions. So if only two condition is satisfied, not first, then problem is known as NP hard problem, right? Yeah. So it is clear, it is evident that the NP complete problems, they cannot be solved in polynomial time. So what is like solution? We cannot like forget the problem. So definitely there are way around it, right? So that is the purpose of the approximation algorithm. This approximation algorithm, in this category, all the problem which can be solved in NP category like NP and NPC. If algorithm is in P category, no need of approximation. Remember, if algorithm can be solved in polynomial, no need of approximation. But on the other hand, if a problem can be solved in NP and NPC, it is taking too much time. So can't we approximate it? Can't we approximate it? And remember, approximation algorithm, they are not giving exact solution. They are giving near optimal solutions, but answer is not exact. It is approximated, right? For example, if you want to calculate cost of a traveling salesperson, right? Suppose optimal cost using the like NP solutions is going to be, let's say, 35, right? But if you are using approximation algorithms, so suppose it is going to be 40. So this is better than this because it is solvable in polynomial time, while this is solvable in NP time. This is solvable in polynomial time. So this is the solution, that what to do. You know, many problem of practical significance, as I said, that are NP complete, right? Yet they are too important to abandon. That means we are not going to skip them. So solution is that, so what is solution? Number one, first solution is if the actual inputs are small, right? An algorithm with exponential running time may be perfectly satisfactory. Yes. If actual inputs are small, then there is no problem. You can use NP problem. Or second solution is that we may be able to isolate important special cases that we can solve in polynomial time. This is the second solution. It is also not very recommended. Third solution is that we might come up with approaches to find near optimal solution. This is the important keyword here. So we are going to get near optimal solution, right? Yeah, we are going to get near optimal solution using approximation algorithm, right? Okay. So and this near optimal solution, they are going to solve the problem into the polynomial time. Okay. So in practice, near optimality is often a good choice. So this kind of algorithms are known as approximation algorithm. So I'm going to define a terms approximation ratio. This approximation ratio is like valid for all the approximations algorithm and very important factor to determine whether approximated solution is better than the better than the polynomial NP solutions, like optimal solution. Okay. So see this. So this approximation ratio is going to be defined like, see, maximum of these terms are this term, C by C star or C star by C, where for maximization problem we know that C star is higher than C, so that this is for maximization. C star is higher than C because we are interested in getting this value greater than or equal to 1. For minimization problem, definitely C star is lower than C. So let's have one problem of this approximation category, that is the vertex cover problem. And the vertex cover means that in a undirected graph we are given an undirected graph, right? This. So we are interested in subset of the vertices such that they can cover the entire graph, right? And you will see that this is two approximation algorithm. This algorithm is in two approximation category. Let's have one example. Yeah. So yeah, suppose like you see, suppose this is the graph, right? So what we are going to cover, let us take B and C. If we take B and C like this arbitrary edge, so remove all the other edges which are incident on either B or C. This is the vertex cover algorithm. So this is incidence, remove it. One edge is incidence on in, remove it, right? So remaining like this is the next, this is the first step. Consider next one EF. So what is incident on E? This is incidence, this is incidence. You got this. Then again take D and G. So how many vertices you took? Only you left A. So what are the number of vertices you have taken? Like B, C, E, D, F and G. These vertices you have taken. So 6 number of vertices by this algorithm is required. On the other hand, if we are interested in getting the optimal solution, suppose we are interested in getting the optimal solution, so it's very easy. Just take C. Once you take C, this will cover this, this will cover this, this will cover this. Clear? And then take let's say BDE. BD we will be giving you the optimal solution. Why? B will take this, B will take this, right? B has taken 2. D will take this maximum, D will take this, and D will take this, and D will take this. This is the one, right? And E will take this one. E will take this and E will take this. So if you just take BDE, see, you just take BDE, it will cover entire graph. How? See, B is covering this, this is covering this, D is covering this, D is covering this, and then E is covering this, E is covering this. So this optimal solution is giving 3 vertices and your approximation solution is giving 6 vertices. This is maximum 2 times. So that is why it is known as 2 approximation algorithm. How? 6 by 3. 6 by 3 is going to give you 2. Other solutions are the traveling salesperson problem. So, this is also one of the solutions. You can also solve TSP using approximation. And approximation will work only if question like solution is going to follow the triangle inequality. Problem is like any problem is following the triangle inequality. See, this is the triangle inequality. I to j if dij less than or equal to dik plus dkj. So how to solve it? Use Prim's algorithm from here one, and then you just take a spanning tree using Prim's algorithm and take the in order traversal. You will see the approximate solution of the TSP. So these are the references. Thomas Corman and Sahani Horowitz. Thank you.